The last light inside a giant star does not fade like a lamp. It gives way at the center, where heat has spent itself, and gravity has waited for millions of years. In less than a breath, the core falls inward. Empty space inside atoms is pressed away. Electrons and protons are forced together until matter changes its name, and what remains is a sphere of neutron-rich matter, so dense that a city-sized shadow could hide it, while its mass still outweighs the sun. This is the quiet edge between a star and a black hole, not a place of fire in the ordinary sense, and not a world with ground in any familiar meaning, but a compact remnant with an iron skin, a warped sky, and layers of matter that no laboratory can hold for even a moment. Its surface glows mostly in X-rays. Its gravity bends light around its rim. Deeper down, atoms loosen, neutrons gather, nuclear matter folds into strange sheets and threads, and a frictionless liquid turns beneath the crust, like a hidden ocean that never slows. Before going further, take a moment to settle in. If this kind of slow space documentary helps the night feel calmer, a like, a subscribe, or a share tells the channel to keep making these long, quiet journeys through the darker parts of the universe. Right where in the world this signal is reaching, and what hour it is there. A room can be dim now. A fan can turn softly. The body can rest in whatever position feels easiest, while the mind follows a star that has already died, and yet still keeps time with impossible precision. The path begins with collapse, but not with noise. It begins inside a giant star, at the moment when the outward pressure fails, and gravity closes its hand. Long before the neutron star exists, there is only a massive star burning in the dark. It is not quiet inside. Deep beneath its bright outer layers, pressure and heat press so tightly together that hydrogen nuclei are forced to become helium, and that act of fusion releases the energy holding the star open against its own weight. For millions of years, the star lives inside this balance. Gravity pulls inward, heat pushes outward. The surface shines because the center keeps fighting to stay alive. The star is far larger than the sun, and its life is much shorter. A smaller star can burn slowly, almost patiently, for billions of years. A massive star spends its fuel with much less restraint. Its core grows hotter. Its layers become heavier. Hydrogen gives way to helium. Helium gives way to carbon and oxygen, and later stages of burning build heavier elements in shells wrapped around the center. The structure begins to resemble a set of nested fires, each one burning a different fuel, each one closer to the final limit. That limit is iron. Iron is different from the elements that came before it. When lighter elements fuse, they release energy, and that energy helps the star resist collapse. Iron does not help in the same way. Fusion involving iron does not give the star a new source of pressure. It takes energy instead. So when the core becomes rich in iron, the old bargain between gravity and heat begins to fail. The star still shines from the outside, but inside, something has already changed. The center stops supporting itself. There is no long fading, no slow settling into darkness. The core has been carrying more and more weight from the layers above it, and once the pressure support is gone, gravity closes in with almost no delay. Matter that once occupied a region thousands of kilometers wide falls inward. Electrons are driven into protons. The familiar architecture of atoms, with its open spaces and delicate separation of charge, is erased under pressure. The particles are forced to combine, and neutrons appear in enormous numbers. This is where the future neutron star begins. During the collapse, the core shrinks with a speed that is difficult to place inside ordinary experience. The outer parts of the star have not yet understood what has happened below them. Light, pressure waves, and motion all need time to travel through the star, but the center has already fallen inward. A mass greater than the sun is being compressed into a space no larger than a city. The scale changes so quickly that the old identity of the star cannot follow it. At the center, the newly formed neutron matter stiffens. It cannot be compressed in the same ordinary way as gas, plasma, or metal. Quantum pressure rises. Nuclear forces resist. The inward fall strikes this resistance and rebounds. A shock wave begins to move outward through the surrounding star, carrying the news of the collapse into the layers that still remain above. Those outer layers are thrown away. The star becomes a supernova, though the word is almost too clean for what is happening. Material that once belonged to a single glowing body is driven outward into space. Heavy elements formed in the star are scattered into the surrounding darkness. Gas, light, radiation, and dust expand away from the center, making a cloud that may one day become part of other stars, other planets, and other quiet worlds. The death of the star does not end its matter. It only changes where that matter will go. At the middle of the expanding cloud, something stays behind. It is small, only in width. In every other sense, it is immense. The remnant core contains more mass than the sun, but its surface could fit inside the span of a city. It no longer burns by ordinary fusion. It no longer has the layered life of a star. It is made of matter pressed so tightly that the empty spaces of atoms have almost vanished. The object is held together by gravity, supported by forces that belong to nuclear physics rather than chemistry. A neutron star has been born. It begins its life hot, dense, and spinning. The collapse that made it also changed its motion. The original star was rotating before it died, and when its core shrank, the rotation was concentrated into a much smaller body. The same spinning motion that was once spread across a vast stellar core is now confined inside a compact remnant. The result is a star that can rotate many times in a single second, carrying the memory of its former size inside its new speed. The surface is not like the surface of an ordinary star. There is no gentle photosphere like the visible skin of the sun. There is a crust forming from matter, under pressures that do not occur on Earth. Beneath it, the density rises toward conditions that press against the edge of what physical theory can describe. The object is not simply a dead star, it is a new state of matter wrapped into the shape of a sphere. Around it, the supernova remnant continues to expand. Filaments of gas drift outward, lit by the energy of the explosion and by the compact source left behind. Over time, the cloud thins, the light fades. The neutron star remains, cooling slowly, rotating steadily, and sending its influence into space through gravity, radiation, and magnetic fields that may reach far beyond the remnant itself. Most stars do not end this way. Some shed their outer layers gently and leave behind white dwarfs. Some cores grow too massive and continue collapsing until a black hole forms. A neutron star exists between those outcomes, in a narrow and strange middle ground. It is not light enough to rest as ordinary stellar ash. It is not heavy enough to vanish behind an event horizon. It survives just before that final boundary. That is why it matters. A neutron star is not only the leftover center of a dead giant, it is a place where matter has been pushed past the familiar forms of the periodic table, where gravity is strong enough to bend light, where time itself runs differently near the surface, and where the smallest change in structure can echo across thousands of light years. The story begins with collapse, but it does not end with destruction. It continues inside the remnant, layer by layer, in matter that still holds the pressure of a vanished star. The first sign that such objects were real did not come from a telescope image. It came as a rhythm, a pulse, a signal arriving again and again from the radio sky, so regular that at first it seemed almost impossible for nature to have made it. In the late summer of 1967, the sign arrived on paper, not as an image of a star, not as a bright point in a telescope, but as a small, repeated mark on a long chart recording from a radio telescope in Cambridge. The instrument itself was spread across a field, built from wooden posts, cables, and wires, arranged to listen to faint radio waves from the sky. It did not look like the polished mirror of an optical observatory. It looked like a patient net laid across the grass. Jocelyn Bell was a graduate student then, working through the data by hand. Each day, The telescope produced long rolls of paper, marked with ink traces. Most of the marks belonged to ordinary radio noise, natural sources, or interference from human technology. Bell learned the texture of the paper sky. She learned what usual noise looked like, and because of that, she noticed when something did not belong. The strange signal was narrow and regular. It appeared for a short interval, then vanished, then returned when the same patch of sky passed over the telescope again. That mattered. A signal from a machine on Earth would not keep time with the stars. This one did. It followed sidereal time, the slow clock of the rotating Earth beneath the fixed background of distant space. The source was not in the field. It was somewhere above it. At first, the signal was only a puzzle. It repeated with an interval of a little more than 1 second, too precise for the ordinary language of stars at the time. Stars were known to flare, pulse, brighten, dim, and erupt, but not like this. The rhythm was clean. A mark, a pause, another mark. The spacing was steady enough to feel almost mechanical, as though something in the sky were sending a beat through the darkness. For a short while, the source carried an informal name that has stayed in the history of astronomy. It was called LGM-1, for Little Green Men. The name was partly a joke, and partly an admission that no comfortable explanation had yet arrived. A natural object that pulsed with such discipline seemed unfamiliar. Still, the sky soon made the answer less theatrical. Bell found another signal like it, coming from a different direction. Then, more appeared. Several separate transmitters scattered across the sky became less likely than a new kind of natural source. The explanation had already been waiting in theory. Decades earlier, astronomers had proposed that the collapsed cores of massive stars might form objects made mostly of neutrons. These objects would be small, dense, and difficult to see directly. If one of them rotated rapidly and carried a strong magnetic field, it could send radiation outward from its magnetic poles. If those poles were tilted away from the spin axis, the beams would sweep around as the star turned. The radio telescope at Cambridge had not found a message. It had found a lighthouse. A pulsar is a neutron star whose beam happens to pass across Earth. The beam does not shine evenly in every direction. It is guided by the magnetic field, shaped near the poles, and carried outward into space. The star rotates, and with each turn the beam crosses the line of sight like a distant lamp passing through a narrow window. A radio telescope receives a flash, then silence, then another flash. The spacing between the flashes is the rotation of the star itself. This is why the first pulsar felt so strange. The clock was not artificial. The clock was a collapsed star. An object only about the width of a city was turning with a steadiness that could be measured across light years. Its signal traveled through cold gas, dust, magnetic fields, and the open spaces between stars before reaching a strip of paper on Earth. The mark on the chart was small. The object behind it was not. The regularity comes from the nature of the remnant. When the giant star collapsed, its rotation did not disappear. The core became smaller, and the spin became faster. The same principle can be seen when a spinning skater draws their arms inward and turns more quickly. But inside a neutron star, the scale is no longer ordinary. A stellar core, once spread across a vast region, becomes a compact sphere. Motion that once belonged to millions of kilometers is held inside a body small enough for a city to cover. Some pulsars turn slowly by neutron star standards, once every few seconds. Others rotate many times each second. The fastest known millisecond pulsars complete hundreds of rotations in the time it takes a human heart to beat once. Their beams cross the galaxy in fine, repeating strokes. To a telescope, they become points of timing rather than points of light. That timing has become one of the quiet instruments of modern astronomy. Pulsars can be used as natural clocks because their rotation is so stable. They do slow over long spans of time, losing energy through radiation and magnetic braking, but the slowing is gradual enough to be modeled. Once that gradual change is understood, any tiny disturbance in the arrival time of the pulses becomes meaningful. Space itself can leave a trace in the rhythm. Astronomers now time pulsars to test gravity. In binary systems, where a neutron star orbits another compact object, their pulses reveal general relativity under stronger conditions than the solar system can provide. Arrays of millisecond pulsars also search for very long gravitational waves, slow ripples in spacetime passing through the galaxy, like a low, nearly silent vibration. There is still something gentle about the original discovery: a field of wires, a student reading paper by hand, a small irregular mark that returned when the sky returned. Before the equations, before the catalogs, before thousands of pulsars were known, there was only that repeated pulse and the patience to notice it. Astronomy often moves forward through great machines and bright images, but sometimes it begins as a rhythm almost hidden in noise. The pulse opened the door. It proved that neutron stars were not only theoretical remnants left behind by dead giants, they were real objects with rotation, magnetic fields, surfaces, interiors, and histories written into the signals they sent. The clock in the radio sky pointed back to a body so dense that ordinary matter had lost its empty spaces. The next step is to leave the distant signal behind and move inward toward the matter that makes such a clock possible. The pulse from a pulsar is only the visible edge of something deeper. Behind each radio flash is a body made from matter that has been pushed out of nearly every form that matter takes on Earth. It is not stone, not metal, not gas, not plasma in the familiar sense. It is what remains when a star has taken the open spaces inside atoms and pressed them almost shut. Ordinary matter feels solid because of forces, not because it is full. A hand resting on a table does not pass through the wood because electrons in the atoms of the hand repel electrons in the atoms of the table. The sensation of hardness comes from that resistance, but inside each atom there is far more open volume than substance. The nucleus is tiny. The electrons occupy regions far away from it by comparison. Most of the atom is space held in shape by quantum rules. A mountain, an ocean, a steel beam, and a living cell all share that same hidden openness. They feel different because their atoms are arranged differently, but the basic architecture is still spacious. Matter on Earth has room inside it. A neutron star begins where that order is broken. During the collapse, gravity does not merely squeeze atoms closer together. It changes the particles that made the atoms possible. Electrons are driven into protons under pressures so high that the two become neutrons. The old separation between nucleus and electron cloud disappears. Atomic structure, the foundation of chemistry, loses meaning. What remains is a compact body of neutrons with a small mixture of other particles, all crowded into a space that would be almost nothing compared with the star that died. This is why the density is so difficult to imagine. It is not simply that the material has been packed tightly, like sand pressed into a jar. Sand still leaves gaps. Even metal still leaves the vast quantum spacing that makes atoms atoms. In neutron star matter, the collapse reaches down into the structure itself and removes the familiar emptiness from the inside out. A single small spoonful of such matter would carry the mass of a mountain range. The image is only a guide, because no spoon could hold it, no surface on Earth could support it, and the material would not remain in that form outside the pressure that created it. Still, the comparison gives the mind a place to rest. The star is small in diameter, but not small in content. It is a city-sized remnant, carrying the weight of a sun. Density changes more than weight. It changes gravity. With so much mass confined inside such a narrow sphere, the space around the neutron star is bent strongly. Light leaving the surface must climb out of that curvature. Its path is no longer the straight line that ordinary intuition expects. Near the star, geometry becomes part of the object. The surrounding darkness is not just empty space around a dense body. It is space shaped by the body. Time is altered as well. A clock close to the surface would not keep the same pace as a clock far away. This is not a failure of the clock. It is the way time behaves in a gravitational field. The stronger the gravity, the more slowly time passes relative to distant observers. Around a neutron star, the difference becomes large enough to matter in the signals astronomers measure. The light loses energy on its way out. X-ray photons that begin near the surface arrive at distant telescopes shifted by gravity, their original energy softened by the escape. That shift is not a flaw in the observation. It is a message. From it, astronomers can learn about the relation between the star's mass and radius, and that relation points back toward the state of matter inside. The compactness also affects the way the star looks. A neutron star can curve light from regions that would normally be hidden behind its edge. Some light from the far side is bent around the star, carrying with it a partial view that ordinary geometry would forbid. The result is a sphere that appears slightly larger and more visible than its real shape alone would suggest. All of this comes from matter with the empty space removed. Yet the phrase is not quite complete. The empty space inside atoms is gone, but the star is not a featureless ball of neutrons. It has layers, and the layers behave differently. At the surface, heavy nuclei can still arrange themselves into a crust. Deeper down, nuclei become unstable. Below that, neutrons move in a liquid state. Density is the beginning of the story, not the end. The pressure increases inward. The outer regions are already beyond any material made on Earth, but the interior continues to grow stranger with depth. At first, the matter keeps enough structure to be called a crust. There are nuclei, electrons, and a kind of crystalline order. It is not a crust like rock. It is closer to a frozen arrangement of charged particles, held down by gravity and nuclear forces. The star is also held together by a balance. Gravity presses inward with enormous force. Something must push back. In ordinary stars, heat from fusion supplies much of that support. In a neutron star, fusion is no longer the answer. The resistance comes from quantum pressure and the behavior of nuclear matter when particles are forced into close quarters. Neutrons cannot all occupy the same state. Forces between them become strongly repulsive at very short distances. These effects help stop the collapse before the object becomes a black hole, as long as the mass remains below the final limit. That balance is narrow. If more mass is added, the star can be pushed beyond what neutron matter can bear. Then the collapse continues, and the surface disappears behind an event horizon. A neutron star survives on the edge before that outcome. It is dense enough to bend light and slow time, yet still able to show a surface to the universe. The pulse from the radio sky, then, is not only a clock, it is a sign from compressed matter. Each rotation carries evidence of a body where atoms no longer have their old spaces, where gravity shapes light, and where time bends close to the surface. To understand the next layer, the journey has to move down to that surface itself, to the thin iron skin that covers the star like a dark, burning shell. The outer skin of a neutron star is not soft light. It is not a glowing atmosphere in the ordinary sense. Beneath the radiation that escapes into space, the star has a surface, and that surface is made from matter pressed into a form that no furnace, laboratory, or planet could create. It is a crust under the rule of gravity so strong that even the idea of roughness changes. The outermost layer is thought to contain heavy atomic nuclei, with iron among the most stable forms near the surface. These nuclei are arranged in a crystalline lattice, held in place by electromagnetic forces and crushed downward by the weight of the star above its own center. Free electrons move between them, carrying heat and charge through the crust. In some ways, it resembles a metal. In every important way, it is unlike any metal on Earth. The pressure gives the crust its character. On Earth, iron can be melted, hammered, bent, rusted, and broken. On a neutron star, iron nuclei sit in a pattern that is locked beneath gravity. The crust is thin compared with the whole star, but it has to hold itself across a body whose surface gravity is far beyond ordinary comparison. It is not simply hard, it is hard because the star gives it no other way to exist. The same gravity that creates the crust also smooths it. Mountains on Earth are possible because rock can support uneven weight. Continental plates push upward. Stone resists. The planet's gravity pulls everything down, but not hard enough to erase every ridge and valley. A mountain range can rise, weather, crack, and stand in the open air for millions of years. On a neutron star, that kind of height is not allowed. Any raised feature is pulled flat almost at once. The surface may be one of the smoothest natural places in the universe. Scaled to the size of an ordinary ball, it would be smoother than a polished sphere. The word mountain still applies, but only because there is no better one. A neutron star mountain may be no higher than a few millimeters, perhaps less, depending on the strength of the crust and the stress it can hold. Across a body with the mass of a star, such a rise is almost nothing, a small wrinkle in an iron skin, yet even a wrinkle matters there. A tiny distortion can change the way the star rotates. It can store stress. It can affect the regularity of the pulses that travel to Earth. The surface looks still from far away, but it is not a passive shell. It is part of the machine that makes a pulsar keep time. The crust forms as the newborn neutron star cools. At first, the remnant is unimaginably hot, filled with energy from the collapse. Neutrinos stream outward. Radiation leaves. The outer regions lose heat faster than the deep interior. As the temperature falls, the nuclei near the surface settle into ordered patterns. The star develops a solid shell around denser matter below. That shell is thin beside the star's diameter, but it separates two very different worlds. Above it lies space, curved by gravity and threaded by magnetic fields. Below it lies matter growing denser with every layer, moving toward the neutron drip region where nuclei begin to lose their identity. The crust is the border between a surface the universe can observe and an interior that can only be inferred. Light leaving the crust carries the first clues. Much of the radiation from a young or heated neutron star emerges as X-rays, too energetic for human eyes but visible to orbiting telescopes built to detect them. The surface does not shine like a familiar star in the night sky. It glows in a harsher, shorter wavelength, sending information through space that can survive the journey to Earth. The magnetic field shapes that glow. Heat does not always travel evenly through the crust. It can move more easily along magnetic field lines than across them, producing warmer and cooler regions on the surface. As the star turns, those hot regions rotate in and out of view. Their brightness rises and falls. A telescope does not see a detailed surface map directly, but it sees the rhythm of the light, and from that rhythm, a map can slowly be reconstructed. The surface is also under strain. The crust may be rigid, but the star beneath it is not perfectly still. The superfluid interior can rotate at a slightly different rate from the crust. Magnetic fields can pull and twist the outer layers. Over long periods, stress builds in the lattice. The crust holds until it cannot hold in quite the same way anymore. Then it shifts. A starquake is not an earthquake placed on a larger stage. It is a change in a crust made from nuclear density matter, under gravity, that allows almost no height, around a body spinning with remarkable steadiness. The movement may be small in distance, but small distances on a neutron star can carry large consequences. A slight rearrangement of the crust can alter the rotation rate by a fraction, producing what astronomers call a glitch in the timing of a pulsar. From Earth, a glitch appears as a sudden change in the pulse interval. The beam arrives a little earlier than expected. The clock has not failed. The star has adjusted itself. Something inside or beneath the crust has shifted, releasing stored rotation or stress into the outer shell. The event may be hidden from direct view, but the pulse records it. In magnetars, where magnetic fields are stronger still, the crust can be placed under even greater tension. Magnetic stress may fracture or rearrange the surface, releasing bursts of X-rays and gamma rays. The most energetic events are rare, and they belong to a special kind of neutron star, but they show how closely the surface is tied to the invisible field around it. The crust is not just a covering. It is where gravity, magnetism, heat, and nuclear matter meet. The surface remains almost perfectly smooth after all of this. Gravity erases the large scars. Heat continues to leak outward. The magnetic field keeps shaping the flow. To a distant observer, the neutron star may look like a point source, a tiny pulse, or a faint X-ray glow. Close to the object itself, the crust is a dark iron landscape without familiar hills, held flat by the weight of a collapsed sun. Below that iron skin, the pressure rises again. The nuclei that still survive in the outer crust are carried downward into conditions where even they cannot remain whole. The ordered lattice begins to give way to a stranger boundary, one where neutrons loosen from nuclei, and the last familiar pieces of atomic matter start to come apart. The iron skin of a neutron star is not cold, it is solid, but it is not quiet in the way cold stone is quiet. Heat moves through it from below, carried outward from the deep interior of the collapsed core. The surface is only the outer edge of a much warmer body, a thin boundary where energy finally escapes into space after passing through matter pressed beyond ordinary forms. A newborn neutron star begins its life with heat left over from collapse. The core has fallen inward, particles have been forced into new arrangements, and the outer star has been thrown away. What remains is not only dense, it is hot with the memory of its formation. In the first moments after birth, temperatures inside the remnant reach levels that belong to nuclear physics more than astronomy. The star is still settling from the violence that made it, and its earliest cooling is dominated by particles that barely interact with matter at all. Those particles are neutrinos. They stream out from the interior, carrying energy away from regions that light cannot easily leave. Photons, the particles of light, scatter again and again inside dense matter. Neutrinos pass through much more freely. In a young neutron star, they become one of the main ways the interior loses heat. For a time, the star cools from within by letting these ghost-like particles escape into space. Later, as the star ages, the surface becomes more important. Heat conducted through the crust reaches the outer layers and leaves as radiation. Much of that radiation is in X-rays, too energetic for the human eye, and too short in wavelength to appear as ordinary starlight. A neutron star in visible light may be faint, sometimes nearly invisible, while in X-rays, it can reveal a warm surface still glowing after the death of the giant that made it. The surface temperature can remain high for a very long time. Even after many thousands of years, the star may still shine in X-rays. After much longer spans, the glow dims, but the cooling is slow because the object is compact and its interior stores enormous thermal energy. It is like a coal from a vanished fire, except the coal is made of nuclear matter, and the fire was a collapsing stellar core. The heat does not leave evenly. A neutron star is not a simple warm sphere radiating with perfect balance. Its magnetic field guides the flow of energy through the crust. Heat can travel more easily along magnetic field lines than across them. This creates warmer regions and cooler regions on the surface, especially near the magnetic poles, where charged particles and field lines focus energy into smaller areas. As the star rotates, those warmer patches move across the line of sight. The X-ray brightness rises and falls. A telescope records the changing light, not as a picture with continents and seas, but as a pulse shape. From that pulse shape, astronomers can infer where the hot regions are and how the star's gravity bends their light. The surface glow becomes a quiet map written in timing and energy. Cooling also gives clues about the hidden core. Different forms of matter lose heat in different ways. If the interior contains only neutrons, protons, and electrons arranged in one set of states, the cooling follows one pattern. If deeper layers contain more unusual particles or phases, the star may cool faster or slower than expected. The temperature seen at the surface becomes a distant trace of what the center may be doing. This is one reason neutron stars are useful to physics. No laboratory can hold their interior pressure. No machine can build a sample of their core and place it on a table. But the star cools, pulses, and glows. Its heat leaves slowly, and that escaping heat carries information from places that cannot be opened. The surface is the visible ending of a path that began far below. There is a softness in the image, despite the harsh physics. A small, star-shaped remnant, dark to ordinary sight, gives off X-rays into the surrounding night. It is not burning like the sun. It is not fusing hydrogen in a steady furnace. It is cooling. The energy is old energy, inherited from collapse, leaking through a crust that formed after the star's original life was over. The glow may last through ages longer than human history. A supernova remnant can fade until its filaments become thin and hard to see, but the neutron star at its center may keep radiating. Young examples can be bright in X-rays. Older ones grow dimmer, their surfaces losing heat gradually, their pulses becoming harder to detect unless magnetic fields or accretion renew the energy output. Some neutron stars are warmed again by matter falling from a companion star. In a binary system, gas can be pulled away from the companion and guided into a disk around the compact remnant. As the gas spirals inward, it gains speed and heat. When it finally reaches the neutron star's surface, the energy released is far greater than ordinary chemical burning. The surface can flare in X-rays as fresh material is compressed and heated. These bursts are not needed for every neutron star, but they show what the surface can do when fed. A thin layer of hydrogen or helium can accumulate under the pressure of the star's gravity. When enough material gathers, nuclear burning can ignite across the layer, producing a short X-ray flash. The event fades, the surface settles, and the process may begin again if more gas continues to fall. Even without accretion, the star's own magnetic field can shape its heat. In magnetars, magnetic energy may warm parts of the crust from within. Stressed fields can shift, twist, and transfer energy into the surface, creating bright patches that slowly fade. The light is not random. It reflects the geometry of the hidden field and the properties of the crust that carries the heat outward. For the listener far away, all of this arrives as data: a curve of brightness, a spectrum of X-ray energy, a slow decline in temperature over years, a pulse changing slightly as the star turns. None of these signals shows the interior directly, yet each one narrows the possible answers. The cooling surface becomes a kind of thermometer, lowered into a place no instrument can reach. Below the glowing iron skin, the pressure keeps increasing. The nuclei that survive in the outer crust are pushed into denser arrangements. Heat still moves through them, electrons still carry energy, and gravity still presses everything inward. But deeper down, the old structure of nuclei begins to fail. At a certain depth, neutrons no longer remain fully locked inside atomic nuclei. They start to loosen, then escape, forming a new layer where atoms begin to unmake themselves. Below the outer crust, the pressure rises into a region where the last familiar pieces of atomic matter begin to lose their hold. The nuclei are still there at first, arranged in a dense lattice, surrounded by electrons, pressed into forms that would never be stable under ordinary conditions. But the deeper the layer goes, the less ordinary even that strange order becomes. The star is moving toward a boundary where atoms no longer remain atoms in any meaningful sense. The boundary is called the neutron drip line. It is not a surface that could be seen. It is not a sharp wall or a change in color. It is a threshold in the behavior of matter, reached when pressure becomes strong enough to make atomic nuclei unable to keep all their neutrons bound. Above this depth, neutrons and protons still sit together inside nuclei. Below it, some neutrons begin to slip free. They no longer belong to any single atom. They become part of the star itself. The word drip sounds gentle, almost too gentle for the place it describes. Nothing is falling like water from a ceiling. The process is quantum and nuclear, happening inside matter so dense that the distances between particles have become extremely small. Yet the word is useful because it gives the mind a simple image. A nucleus is squeezed until it can no longer hold everything inside. Neutrons leak out into the spaces between nuclei, forming a sea around the remaining charged structures. This changes the identity of the crust. In the outer layers, the material can still be described as nuclei and electrons, even if the nuclei are packed under extraordinary gravity. In the inner crust, the nuclei are immersed in free neutrons. The crystal lattice remains, but it is no longer alone. It is surrounded by a fluid of particles that have left the old architecture of atoms behind. The cause is pressure. As depth increases, the nuclei become richer in neutrons. They are forced into arrangements far beyond the stable isotopes known on Earth. In ordinary laboratories, a nucleus with too many neutrons tends to decay, shedding energy, and returning toward a more stable form. Inside the neutron star, the surrounding pressure changes the accounting. The dense environment makes neutron-rich nuclei possible, at least for a while. Then even that is not enough. Extra neutrons can no longer stay bound, and the drip begins. This is one of the quiet thresholds that make neutron stars so valuable to physics. It is a place where the periodic table starts to fade. The names of elements still matter in the outer crust, where iron and heavier nuclei can be discussed as recognizable structures. Deeper down, the question changes. It is no longer only which element is present, but whether the idea of an element still applies. The free neutrons do not behave like a gas in the usual sense. They are packed too closely and ruled too strongly by quantum mechanics. They move through the inner crust as a degenerate fluid, meaning their behavior is controlled by the available quantum states rather than by temperature alone. Heat is still present, but density has become the stronger law. The particles fill the possible states in a way that resists further compression. Around them, the remaining nuclei continue to change. They grow larger and more neutron-rich with depth. Electrons move through the lattice, balancing charge and carrying energy. The whole region becomes a mixture. Charged nuclear clusters, free neutrons, and electrons, all held under gravity, all shaped by forces that are normally hidden inside atomic nuclei. No laboratory can recreate this full environment. Experiments on Earth can study neutron-rich nuclei for brief moments. Particle accelerators can produce unstable isotopes and measure how they decay. Nuclear theory can describe how forces behave at short range. But the inner crust of a neutron star combines all of these ingredients with gravity and pressure on a scale that no experiment can contain. The drip line inside the star is therefore understood through a mixture of observation, theory, and careful modeling. It is also connected to the signals seen from outside. The inner crust is not visible, yet it affects how the star stores stress, how heat travels, and how rotation couples between the solid crust and the fluid layers below. In pulsars, small timing changes may depend partly on this region. The free neutrons can participate in superfluid motion, and their interaction with the crust may help explain why a spinning neutron star sometimes glitches, suddenly changing its rhythm by a tiny amount. The boundary is narrow compared with the whole star, but it carries a large meaning. Above it, matter still keeps a memory of atoms. Below it, that memory weakens. The star is not simply compressing the same material more and more tightly. It is changing what material means at each depth. There is a slow visual way to imagine it. Near the surface, the crust is a dark, crystalline plane of nuclei and electrons. Farther down, the spaces between the nuclei begin to fill with loose neutrons, like a fog settling into a forest of charged particles. Deeper still, the fog thickens until it becomes one of the main substances of the layer. The nuclei remain, but they are no longer the whole story. The star is becoming less like a solid object and more like a layered quantum medium. The drip line also shows why a neutron star is not made entirely of simple neutron matter from surface to center. Its name can make the object sound uniform, as if the whole star were one single substance. The truth is more delicate. The outer crust has nuclei. The inner crust has nuclei plus free neutrons. Lower regions form strange shapes. Deeper regions flow. The star is built from transitions, and the neutron drip line is one of the first. At this depth, chemistry is almost gone. Chemical bonds rely on electrons arranging themselves around nuclei. Here, electrons are not forming familiar shells and molecules. They are squeezed into a dense background, while nuclei are forced into compositions that would fall apart anywhere else. The language of minerals, rocks, metals, and molecules no longer fits. Nuclear physics has taken over from chemistry. Still, the change is not chaotic. The matter follows rules. The nuclear force, the electromagnetic force, gravity, and quantum pressure all contribute to the pattern. The inner crust is strange, but it is not random. It has structure, and that structure shapes what happens below. The free neutrons that appear here lead to the next quiet surprise. Away from a nucleus, a neutron is not normally stable. In ordinary empty space, it would decay after a short time, changing into other particles. Inside the neutron star, surrounded by dense matter and filled quantum states, that decay can be blocked. The particles that should not last are held in place by the conditions around them, and the star preserves them in a form that could never survive alone. A free neutron, away from a nucleus, is usually a temporary thing. In open space, with room around it and no surrounding pressure to change its options, it does not remain itself forever. After a short lifetime, it decays. It becomes a proton, an electron, and an antineutrino, releasing the small difference in energy that nature allows it to lose. That process has been measured carefully on Earth. It is part of the ordinary behavior of particles when they are alone. Inside the inner crust of a neutron star, the situation is different. The neutrons that drip out of nuclei are free in one sense, because they no longer belong to a particular atomic nucleus. They move through the spaces between the remaining nuclear clusters, filling the layer like a dense quantum fluid, but they are not free in the way a neutron in empty space is free. They are surrounded by other particles. They are pressed into an environment where almost every possible low-energy state is already occupied. The star does not give them the same choices. The key rule is the Pauli exclusion principle. It says that two identical fermions cannot occupy the same quantum state at the same time. Fermions include electrons, protons, and neutrons. The rule sounds abstract, but it is one of the reasons ordinary matter has structure at all. It helps atoms keep their size. It helps compact stars resist gravity. In a neutron star, the same rule operates in a much denser place. A simple image helps. Imagine a theater where every seat is filled. A new person cannot sit unless a seat opens. In the neutron-rich matter below the drip line, many of the available quantum seats for the particles produced by neutron decay are already taken. For a neutron to decay, the proton and electron that appear afterward must have allowed states to occupy. If those states are blocked, the decay cannot proceed in the ordinary way. The neutron may have a path in empty space, but inside the star, that path is closed. This is sometimes called quantum blocking. It is not a wall made of matter. It is a restriction created by the rules of quantum states. The decay products have nowhere acceptable to go, so the decay is suppressed. A particle that would be unstable in a laboratory can become stable inside a neutron star because the environment changes the allowed outcomes. The idea is quiet, but it is deeply important. The neutron star depends on neutrons remaining neutrons. If large numbers of free neutrons decayed as they would in empty space, the composition of the inner crust and deeper layers would change. More protons and electrons would appear. Charge balance, pressure, and energy would shift. The star would not have the same structure. Its ability to resist gravity would be altered. Instead, the dense environment holds the particles in place. The neutrons fill their states. The surrounding matter fills other states. The whole layer becomes a locked arrangement, not frozen in the ordinary sense, but constrained by quantum rules. Change is not impossible, yet many familiar kinds of change are forbidden. This is one of the ways neutron stars turn small-scale physics into something astronomical. The Pauli exclusion principle was developed to describe particles and atoms. Inside a neutron star, it helps support a body with more mass than the sun. A rule about quantum states becomes part of the architecture of a star. It is the same law, working without regard for scale. There is also a difference between pressure from heat and pressure from degeneracy. In a gas on Earth, pressure often comes from particles moving rapidly because they are warm. Heat makes them strike the walls of a container. In degenerate matter, pressure comes from the fact that particles cannot all fall into the same lowest states. Even if the material cools, the pressure remains. The particles are crowded by quantum law, not merely by temperature. This means the inner crust can stay supported even as the star loses heat. The neutron star cools through neutrinos and X-rays, but the degenerate pressure does not simply fade away with the temperature. A cooling neutron star remains dense and compact because its support is not the same as the hot pressure inside an ordinary star. The old stellar furnace is gone. A different kind of resistance has taken over. The free neutrons in the inner crust may also begin to behave collectively. At sufficiently low temperatures compared with their density, they can pair in ways that lead towards superfluidity. The word low must be handled carefully here, because the star is still hot by earthly standards. But compared with the enormous energy scale of dense nuclear matter, the conditions can allow quantum pairing. The inner crust becomes not only a place where neutrons are stable, but a place where they may move with unusual coherence. That coherence matters for pulsars. The solid crust rotates. The neutron fluid below can rotate in a different way, organized through tiny quantized vortices. Those vortices may interact with the lattice of nuclei in the inner crust, pinning in place for long periods before shifting. When they do shift, angular momentum can be transferred to the crust. The pulse timing changes slightly. A distant telescope receives the evidence as a glitch. The event is small in timing, but the message is large. It means that the radio rhythm reaching Earth is affected by a hidden sea of neutrons below the crust. The pulse is not only a beam crossing space, it is also a record of how quantum matter moves inside the star. The inner crust, therefore, becomes a meeting place. Above it lies the hard outer shell, the smooth surface, and the magnetic field reaching outward. Below it lies denser matter, stranger shapes, and eventually the fluid core. Within it, free neutrons exist in conditions that allow them to remain stable far beyond their ordinary lifetime. They are held not by a container, but by density, pressure, and the filled seats of quantum mechanics. The deeper layers press onward. The remaining nuclei do not simply continue as round clusters forever. As the pressure grows, the competition between nuclear attraction and electric repulsion begins to reshape them. Blobs stretch into rods. Rods flatten into sheets. Spaces invert. Matter keeps its order, but the order becomes unfamiliar. Below the region of stable free neutrons, the star approaches one of its strangest layers, where physics gives nuclear matter shapes, named after food from a quiet kitchen. The names sound almost too ordinary for the place they describe. Gnocchi, spaghetti, lasagna. These are not jokes added after the fact, to make dense physics easier to remember. They are the names physicists gave to shapes that appear in the deep crust of a neutron star, where nuclear matter is squeezed between forces that do not usually have to negotiate so closely. Above this region, nuclei can still be imagined as clusters, crowded and neutron-rich, surrounded by loose neutrons and electrons. Deeper down, the pressure grows until those clusters cannot keep their rounded forms. The distance between them becomes too small. The nuclear force, which binds protons and neutrons together at very short range, begins to compete with the electric repulsion between protons. One force wants matter to gather. The other resists the gathering of charge. Gravity presses from above and all around. The result is not disorder, it is geometry. At first, the nuclear clusters may form rounded droplets, dense islands floating inside the sea of neutrons. These are the shapes called gnocchi. They are not pasta in any chemical sense. They are nuclear matter, made from protons and neutrons, with electrons and free neutrons filling the surrounding region. The name simply gives the shape a familiar anchor. Small, rounded pieces, suspended in a medium that is itself far denser than anything on Earth. With increasing depth, the droplets stretch. Pressure favors contact. The clusters elongate into rods, and the rods run through the inner crust like narrow threads of nuclear material. This is the spaghetti phase. Each strand exists at a scale far below anything a microscope could see directly. It is smaller than an atom, smaller than the familiar boundaries of chemistry, yet it may extend through the matter as a repeated pattern, a hidden texture inside the star. Below that, the rods flatten. Matter spreads into sheets. These sheets are the lasagna phase, layers of dense nuclear material separated by neutron-rich regions. The image is quiet and almost domestic, but the material is not soft. It is held together by the strongest forces known in nature, under pressure that has pushed matter beyond its ordinary boundaries. A sheet of nuclear pasta is not a surface that could be touched. It is a phase of matter, a pattern in the arrangement of particles. The geometry can then invert. Instead of dense strands inside a neutron sea, void-like regions can appear inside denser nuclear matter. Tubes of lower density run through the material. Then bubbles form, hollow regions enclosed by the surrounding nuclear phase. These are sometimes called antipasta, because the relationship between dense matter and open space has turned inside out. Even here, the word open must be used carefully. The empty regions are not empty in the earthly sense. They are simply less dense than the matter around them. This layer is expected to be thin compared with the whole star. Yet thin does not mean light. In a neutron star, a narrow band can contain more mass than many planets. The scale of depth and the scale of mass no longer match ordinary intuition. A layer that could be crossed quickly in a human landscape may, in the star, carry an amount of matter that belongs to worlds. No telescope has photographed nuclear pasta. It lies below the surface, hidden beneath the crust, and inside a body only a few tens of kilometers wide. The evidence comes from nuclear theory, computer simulations, and the need to explain how matter behaves when squeezed toward nuclear density. Different calculations do not agree on every detail. The exact thickness, transitions, and mechanical properties depend on the model used for the nuclear force. But the appearance of these shapes is not a single fragile prediction. They arise again and again when the equations are pushed into this region. That repeated appearance is why the layer is taken seriously. It is not decoration. It may affect how the star cools, how heat moves upward, how the crust breaks, and how the magnetic field passes through dense matter. The shapes change the transport of energy. Rods and sheets do not conduct heat and electricity in the same way in every direction. A star with nuclear pasta may carry heat differently through its lower crust than a star without it. The layer may also influence neutrinos. These particles carry energy away from young neutron stars, slipping through matter more easily than light. The arrangement of the pasta can scatter neutrinos or let them pass in ways that alter the cooling of the star. A hidden texture in the crust may therefore leave a faint signature in how quickly the surface glow fades over time. Its strength is another reason the layer matters. Nuclear pasta may be among the strongest materials allowed by physics. In the lasagna and spaghetti phases, nuclear forces connect matter across extended structures. Breaking such a pattern is not like cracking rock or bending metal. It means deforming matter held together by the same force that binds atomic nuclei. Simulations suggest that it can store enormous stress before yielding. Stored stress has consequences. A pulsar that rotates steadily for years may suddenly change its timing by a tiny amount. Some of those glitches may involve the crust, the inner crust superfluid, and the pasta layer together. The nuclear pasta could act as part of the coupling region between the solid outer shell and the fluid interior below. It may hold, resist, and then allow motion to shift through the star. The layer is small, hidden, and nameless to the eye, but it may help decide how the whole object behaves. There is a calm strangeness in this part of the neutron star. Matter has not dissolved completely. It has not yet become the deep liquid of the outer core. Instead, it forms patterns, as if the star pauses between solid and fluid, between nuclei and continuous matter. The shapes carry familiar names only because language has to borrow from somewhere. Under those names, the physics remains far from any kitchen, any mineral, any material made by hand. Below the pasta, the organized shapes begin to give way. Nuclei lose their boundaries more fully. The sea of neutrons becomes dominant. The matter no longer holds itself as rods or sheets. It begins to flow, but not like water, oil, or molten rock. It enters a quantum state, where motion can persist without ordinary friction, and the hidden interior of the neutron star becomes a liquid that does not slow down. Nuclear pasta sits in darkness, far below the iron surface, carrying stress in a way no ordinary material can imitate. It is not strong because it is cold. It is not strong because it is made from atoms arranged in a clever pattern, the way diamond is strong. It is strong because the usual boundary between atomic structure and nuclear structure has been crossed. The force holding it together is not mainly chemistry. It is the force that binds the centers of atoms themselves. In ordinary solids, strength comes from electron bonds. Atoms share, exchange, or arrange their outer electrons in patterns that resist being pulled apart. Steel, diamond, ceramics, and other hard materials all depend on this outer architecture of atoms. The nuclei inside them remain separate, distant from one another on the scale of nuclear physics. The strong nuclear force is locked away inside each nucleus and does not reach across the solid in any ordinary way. In nuclear pasta, the situation has changed. The matter is so compressed that neighboring nuclear structures are close enough for nuclear forces to shape the larger pattern. Rods, sheets, and inverted bubbles are not held together like crystals in a rock. They are held together by matter, in a state where the nuclear force has become part of the structure of the layer itself. This gives the material a resistance to deformation that has no close comparison on Earth. Simulations suggest that the pasta layer can store enormous strain before it breaks or rearranges. The word break must be used carefully. Nothing there cracks like glass or stone. A fracture in this layer would be a reorganization of nuclear matter under pressure, a shift in geometry inside a star. The distance moved may be tiny. The stored energy may still be large enough to alter the timing of the whole object. This is where the hidden interior begins to speak through the surface. A pulsar turns with great steadiness, but not perfect silence. Over time, it loses rotational energy. Its magnetic field carries energy away. Its beam sends radiation into space. The rotation slows by a very small amount, usually in a smooth and predictable way. Astronomers can measure this slowing with care, pulse after pulse, year after year. Then, sometimes, the rhythm changes. A glitch is a sudden small increase in the rotation rate of a pulsar. The pulse arrives just a little earlier than the model predicted. The change can be brief and subtle, but it is real. Afterward, the star may slowly relax toward its earlier pattern or settle into a new one. From Earth, it appears as a tiny irregularity in a clock that is otherwise among the most stable natural clocks known. The cause is not fully settled for every glitch, but one leading picture involves the star's layered interior. The solid crust rotates. Beneath it, neutron superfluid can rotate through quantized vortices, each one carrying a fixed amount of angular momentum. These vortices may become pinned to structures in the inner crust, including the lattice and possibly the pasta layer. While the outer crust slowly loses rotational energy, the pinned superfluid can hold on to a slightly faster motion. For a long time, nothing visible happens. Stress builds in the coupling between the layers. The crust slows. The hidden fluid does not slow in quite the same way. Vortices remain caught. The system stores a mismatch. At some point, part of that stored rotation is released. Vortices unpin or shift. Angular momentum moves outward into the crust. The crust spins slightly faster. The beam keeps sweeping through space, and a telescope receives the next pulse a little sooner than expected. A glitch is small on a chart. Inside the star, it is the record of a rearrangement across matter no eye can see. The pasta layer may matter because it sits in the right place. It lies between the more familiar crust above and the deeper fluid regions below. It can resist motion, store stress, scatter particles, and affect how vortices interact with the solid structure around them. It may act almost like a hidden coupling surface, not a smooth boundary, but a textured region where rotation, heat, and nuclear geometry meet. Its strength allows it to hold tension. Its shape may make that tension uneven. Rods and sheets do not respond the same way in every direction. A layer of lasagna-like sheets may conduct, flex, or resist differently along one direction than another. Spaghetti-like rods may provide a different path for motion and stress. The star's interior is not only layered by depth, but also textured by geometry. This texture may influence more than glitches. It may affect how the star vibrates after a disturbance. It may change how heat leaks from the interior toward the surface. It may alter how neutrinos escape from young neutron stars, shaping the cooling curve seen thousands of years later. A layer only a fraction of the star's radius can leave traces in timing, temperature, and radiation. The difficulty is that the evidence is indirect. Nuclear pasta cannot be sampled. It cannot be brought into a laboratory. It cannot be photographed by a telescope. Its existence is inferred from the physics of matter near nuclear density and from the behavior of neutron stars that carry the consequences of that physics. Scientists test the idea by building models, comparing them with pulsar glitches, cooling observations, and constraints from gravitational waves. Each observation narrows the possible forms of the hidden matter. A pulsar that glitches often may require a different interior coupling than one that hardly glitches at all. A young neutron star that cools faster than expected may hint at particle processes or structures that let energy escape more easily. A merger between neutron stars may reveal how stiff or soft the dense matter becomes when the entire star is deformed by another star's gravity. The pasta layer is therefore both material and message. It is part of the star, but it is also part of the code by which the star can be read. There is a kind of stillness in imagining it. Under the smooth surface, beneath the X-ray glow, below the region where neutrons first drip from nuclei, the matter gathers into silent shapes, droplets stretch into rods. Rods flatten into sheets. Sheets give way to holes and inverted forms. The pattern is hidden, but it may decide how the star's pulse shifts by a fraction after years of steadiness. A small timing change crosses space. It reaches a radio telescope as a corrected rhythm, a tiny arrival too early. Behind that small mark lies a dense layer of matter stronger than anything built on Earth, holding and releasing stress inside the remnant of a dead giant star. Below that strongest hidden layer, solidity begins to fade. The organized nuclear shapes dissolve into a deeper ocean of particles. The star does not become simple there. It becomes more fluid, more quantum, and less familiar. Matter that has been pressed beyond atoms begins to flow without ordinary friction, carrying the rotation of the star in vortices that can persist for ages. Below the pasta layer, the last solid shapes begin to lose their edges. The rods and sheets of nuclear matter give way to a deeper region where individual nuclei no longer remain as separate structures. The pressure has become too high for that. Matter no longer holds itself as a lattice or as a set of strained shapes. It becomes a dense liquid of mostly neutrons, with a smaller population of protons and electrons moving through it. The word liquid can be misleading here. This is not liquid in the everyday sense of rain, seawater, or molten rock. It has no surface to ripple under wind. It does not pour from one place to another. It exists under a gravity and pressure so large that the ordinary images of flowing matter are only faint comparisons. Still, it is not a rigid solid. It can move. It can carry rotation. It can respond to the crust above it and to the magnetic fields threading the star. At these densities, the neutrons enter a quantum state called Superfluidity. A superfluid is a liquid that flows without ordinary friction. Laboratory superfluids can be made from helium cooled close to absolute zero. Under those conditions, helium stops behaving like a normal fluid. It can creep along surfaces, pass through narrow openings, and keep moving in ways that seem to ignore the usual loss of energy. Inside a neutron star, superfluidity does not come from earthly cold. The star is still hot by human standards, with temperatures that would destroy any ordinary material. But the energy scale of dense nuclear matter is so high that the interior can be effectively cold compared with the motion and pairing of the particles inside it. The neutrons can pair together, not as chemical partners, but through quantum interactions. When enough pairs move in a coordinated state, the fluid loses ordinary internal resistance. This does not make the interior calm in the simple sense. A superfluid can be strange precisely because it is so ordered. It cannot rotate like water in a bowl, with every layer sliding past the next. Rotation in a superfluid is carried in tiny organized vortices. Each vortex is a narrow line around which the fluid circulates. The rotation comes in fixed units, as if the liquid is allowed to spin only in counted threads. A neutron star can contain an enormous number of these vortex lines. They stretch through the superfluid interior, aligned roughly with the rotation of the star. The crust above turns as a solid shell. The superfluid below carries its own stored rotation in this forest of vortices. The two are connected, but not always perfectly locked together. Over long spans of time, the outer crust gradually slows. The star loses rotational energy through radiation and magnetic braking. The beam still sweeps across space, but each turn takes a fraction longer than before. Deep inside, the superfluid can resist that slow change. Its vortices may become pinned to structures in the crust or inner crust, held in place by interactions with the nuclear lattice and the pasta layer above. This creates a hidden difference. The crust slows a little. The superfluid keeps more of the old spin. The mismatch can build for years. Nothing obvious appears at the surface. The pulse continues. The timing remains nearly perfect. Then, when enough stress has accumulated, vortices can unpin and move outward. Angular momentum flows from the superfluid into the crust. The crust speeds up slightly. Far away, a radio telescope records a glitch. In this way, the liquid interior can touch the radio sky. A tiny shift in vortex motion, buried deep inside a star, becomes a small change in pulse timing after crossing hundreds or thousands of light years. The path from interior motion to telescope data is long, but it is real. The pulse carries news from a place that cannot be seen. The superfluid also changes how heat moves and how the star cools. Pairing between neutrons can suppress some neutrino emission processes and allow others. Since neutrinos carry energy out of the star, the presence or absence of superfluidity affects the cooling curve seen from outside. A young neutron star cooling faster or slower than expected may therefore carry evidence for particle pairing in its core. Surface temperature becomes a trace of a hidden quantum ocean. There are other layers in the same region. The protons, though far fewer than the neutrons, may also pair. When they do, they can become superconducting. A superconductor carries electric current without ordinary resistance. In earthly laboratories, superconductors usually require low temperatures or special materials. In the neutron star, pressure and density create the conditions in a place still filled with heat. The coexistence of neutron superfluidity and proton superconductivity makes the outer core one of the strangest known interiors in astrophysics. The neutrons carry rotation through vortices. The protons carry electric currents with little or no resistance. Electrons help maintain charge balance and move through the dense medium. Magnetic fields pass through this mixture in complicated patterns, sometimes arranged into thin tubes of magnetic flux inside the superconducting component. The star is therefore not a simple spinning ball. It is a layered quantum system. The solid crust, the nuclear pasta, the neutron superfluid, and the superconducting proton fluid are tied together by gravity, rotation, magnetism, and heat. Each part responds at its own pace, but the whole object must remain one star. When one layer shifts, another layer feels it. This is why neutron stars are so useful and so difficult. Their signals are visible, but their causes are hidden. A pulse that arrives early may involve vortex motion. A change in surface heat may involve particle pairing. A magnetic flare may involve stresses in the crust and currents below. No single observation opens the interior completely. Each one reveals a narrow line. Below the superfluid outer core, the pressure continues to climb. The particles are pushed closer still. The question becomes less about how neutrons flow and more about whether neutrons remain the right description at all. Before reaching that deepest uncertainty, the currents carried by the smaller population of protons deserve their own quiet passage, because those currents help sustain the magnetic field that makes many neutron stars visible across the galaxy. The protons in the outer core are few compared with the neutrons, but they are not minor. They carry electric charge, and charge gives them a different role inside the star. Where neutrons shape much of the mass and rotation, protons help shape the magnetic life of the remnant. In the dense liquid below the crust, they can enter a state where electrical resistance disappears. On Earth, resistance is one of the ordinary costs of electricity. A current moving through a wire loses some energy as heat. The wire warms. The current fades if it is not maintained. Even carefully built systems must account for this loss. A superconducting material is different. Once a current moves through it, the current can persist without ordinary resistance, because the particles carrying charge have entered a shared quantum state. In laboratories, superconductivity usually requires carefully prepared conditions. Materials are cooled until thermal motion no longer disrupts the paired state of the charged particles. The temperatures are close to absolute zero for many classic superconductors, and even high-temperature superconductors remain cold by ordinary standards. The idea of superconductivity at the heat of a neutron star sounds wrong at first. The outer core is far hotter than anything on Earth could survive. But the comparison is misleading. Temperature is only one part of the story. In the core of a neutron star, density is so high and particle energies are so large that pairing can occur under conditions that do not resemble a laboratory. Protons can form pairs through the dense nuclear medium. Once paired, they behave collectively. The charged fluid can carry current with little or no resistance, even in a place that is still glowing with the stored heat of a collapsed star. This superconducting proton fluid changes the magnetic field from the inside. A magnetic field is tied to moving electric charge. In ordinary matter, currents lose energy and decay unless they are sustained. In a superconducting region, current can last for immense spans of time. The magnetic field supported by those currents can therefore remain anchored inside the star long after the supernova light has faded. The field is not a thin decoration on the surface. It reaches inward. It is rooted in the behavior of charged particles below the crust, shaped by currents in dense matter, and twisted by the star's rotation. It rises through the crust, bends around the surface, and opens into the magnetosphere, the region of space controlled by the star's magnetic influence. In an ordinary pulsar, the magnetic field may be trillions of times stronger than the field felt at Earth's surface. In a magnetar, it can be stronger still. The number is less important than the effect. Near such a star, matter does not move as it would in empty space. Charged particles follow field lines. Radiation is guided. Heat moves through the crust in preferred directions. The surface develops hot regions where energy is carried upward more efficiently. The field also helps create the beam. Charged particles near the magnetic poles are accelerated along curved field lines. As they move, they radiate. The radiation forms narrow beams that sweep around with the spinning star. When one of those beams crosses Earth, a radio telescope may receive the pulse. The signal that began as a small mark on paper is therefore connected to a charged quantum fluid deep below the surface. The path is long, but the chain is continuous. Proton pairs carry currents. Currents sustain magnetic fields. Magnetic fields guide particles. Particles produce beams. Beams cross space. A telescope receives a pulse. A process hidden inside a dense star becomes a rhythm measured in an observatory. Superconductivity also changes how magnetic fields behave inside the star. In some types of superconductors, magnetic flux does not pass smoothly through the material. It is arranged into many narrow tubes, each carrying a fixed amount of magnetic flux. If the proton fluid in a neutron star behaves this way, the magnetic field inside the core may be divided into tiny flux tubes. These tubes can interact with the neutron superfluid vortices that carry rotation. That interaction may be important. Vortices and flux tubes can pull on one another, pin to one another, or resist moving past one another. The star's rotation and magnetic field are then coupled at a deep quantum level. A change in spin may affect magnetic structure. A change in magnetic stress may affect the crust. The hidden interior becomes a place where motion and magnetism are woven together, not as a metaphor, but as physics. This coupling may help explain why neutron stars evolve in different ways. Some become ordinary pulsars, gradually slowing as they radiate energy. Some, in binary systems, are spun up again by matter, from a companion, and become millisecond pulsars. Some are born or transformed into magnetars, where magnetic energy dominates the surface activity. The interior currents and fields are part of the difference, though the full history of each star depends on birth mass, rotation, cooling, and the field inherited from the collapse. The magnetic field is also slowly changing. Even if superconducting currents can persist, the crust above them can move, crack, or rearrange. The field can diffuse, twist, and decay over long time spans. In magnetars, this decay may heat the crust and power X-ray emission. Magnetic energy becomes surface light. A field, buried in dense matter, leaves a trace in the glow seen by a telescope. There is no simple boundary where the interior ends and the magnetosphere begins. The star behaves as one connected system. The outer core holds superconducting currents. The crust conducts heat and electricity. The surface radiates X-rays. The magnetosphere gathers charged particles into streams. The pulse is the outermost expression of all those linked layers. This makes the neutron star feel less like an object and more like a closed circuit made by nature. No wire was laid. No engine was built. Yet a current can flow for longer than civilizations last. A field can hold its shape across ages, and a beam can sweep the galaxy with steady timing. The next part of the journey follows that beam outward. The magnetic field that begins in the deep charged fluid does not remain hidden. Around some neutron stars, it becomes the most powerful visible feature of the entire object, strong enough to alter the path of particles, shape the surface glow, and turn a dark remnant into a lighthouse measured across the galaxy. The magnetic field that begins inside the star does not stay buried. It rises through the crust, passes through the surface, and fills the space around the neutron star with invisible structure. In an ordinary star, light can often be described as leaving a hot surface and traveling outward. Around a magnetar, the journey of light is less simple. The magnetic field is so strong that it changes the environment the light must cross. A magnetar is a neutron star whose magnetic field dominates much of its behavior. Its surface may be hot in X-rays. Its crust may be under stress. Its magnetosphere can hold charged particles in patterns shaped by field lines rather than by ordinary motion through space. The star may appear as a point to a distant telescope, but the point is surrounded by a magnetic geometry far larger than the body itself. This geometry can be studied through polarization. Light is a wave, and polarization describes the direction in which that wave vibrates as it travels. Ordinary light from many sources is mixed, with many vibration directions blended together. Polarized light has an organized preference. It carries a direction, and that direction can be changed by the material or fields the light passes through. For a magnetar, that direction matters. X-rays leaving the surface and moving through the magnetosphere can become polarized by the magnetic field. The field does not need to be seen directly. It leaves its imprint on the orientation of the escaping light. A telescope that can measure X-ray polarization is therefore not just measuring brightness. It is reading a faint directional memory carried by the photons. IXPE, the Imaging X-ray Polarimetry Explorer, was built for this kind of measurement. It observes not only how many X-rays arrive from a source, and not only their energy, but also the way their electric fields are aligned. For neutron stars and black holes, this opens a different kind of window. The shape of light becomes part of the evidence. One of the important targets was the magnetar 4U0142 plus 61, a compact object in the constellation Cassiopeia. The star is far beyond the solar system, but its X-rays carry information from the surface and the region just above it. When IXPE measured those X-rays, the polarization pattern showed that the magnetic field and the surface were not acting like an ordinary atmosphere around an ordinary star. The results suggested something stark. The magnetar may have a solid surface without a thick atmosphere above it. Instead of X-rays emerging from a deep gaseous layer, they may be coming from a condensed crust or a very thin region close to the surface, shaped strongly by magnetic fields. The surface, in this picture, is not hidden beneath familiar air. It is exposed to space, a magnetic solid radiating through its own field. The image is quiet and severe. A dense star, only the size of a city, holds a crust under immense gravity. Above that crust, the magnetic field rises in loops and arcs, too strong to behave like the fields known on Earth. X-rays leave the surface and pass through that region. As they travel, their polarization is altered. The light reaches a telescope after thousands of years in space, still carrying the orientation given to it near the star. This is one reason magnetars are useful. They allow physics to be tested in conditions that cannot be made in a laboratory. Strong magnetic fields affect the quantum vacuum itself. Empty space is not empty in the deep sense. Quantum fields are still present, and in extreme magnetic conditions, those fields can change how light propagates. The effect is small in ordinary places. Around a magnetar, it may become measurable. The surface and the magnetosphere are tied together. Heat rises through the crust more easily along magnetic field lines than across them. This can create hot regions near magnetic poles or along preferred paths. As the star rotates, those regions move into and out of view. Their X-ray signal changes with the spin. The polarization can change as well, because the observer receives light from different magnetic angles during the rotation. The pulse is therefore layered. Brightness gives one kind of information. Energy gives another. Polarization gives a third. A single magnetar can be studied through how much X-ray light arrives, how energetic that light is, how its intensity changes with rotation, and how the direction of its wave vibration shifts. Each measurement touches a different part of the same hidden structure. The crust below the emission is also affected by the field. Magnetic pressure can stress the solid surface, twisting it slowly over time. In some magnetars, this stress may help power bursts and long-lived X-ray activity. The field stores energy. The crust resists. Heat and radiation mark the places where that energy moves outward. The visible X-ray glow is only the surface sign of a deeper magnetic system. Still, the observations do not make the star simple. A polarization pattern can support one model and weaken another, but it does not remove every uncertainty. The surface composition, the exact field geometry, the presence or absence of a thin atmosphere, and the way radiation changes as it passes through the magnetosphere, all remain active questions. The honest answer is that the light has narrowed the possibilities, not ended them. That is enough to matter. For a long time, magnetars were understood mainly through their power. Strong fields, bright bursts, intense X-ray emission. Polarization adds a quieter form of knowledge. It asks not only how bright the star is, but how the light is arranged. It studies the angle of the wave after it has crossed a region where magnetic fields may reshape the rules of propagation. The star becomes readable, in a more delicate way. The magnetic field also connects back to the pulsar beam. In ordinary pulsars, field lines guide particles into narrow streams that radiate as the star rotates. In magnetars, the same idea is present, but the field is stronger and more twisted. The magnetosphere can hold more energy, and the surface can respond more directly to magnetic stress. The beam, the glow, the bursts, and the polarization all belong to the same magnetic architecture. A neutron star without a strong field would still be dense, hot, and strange. A magnetar adds another layer. It turns the surrounding space into part of the object. The star does not end at the crust. Its influence continues outward through field lines, charged particles, and polarized X-rays. The body is small, but the magnetic structure around it is wide and active. From far away, the observation is gentle. A detector in orbit receives individual X-ray photons. Their energies are counted, their arrival times are recorded, their polarization directions are measured. From those small events, repeated over and over, the shape of an unseen magnetic field begins to appear. The next signal to follow is not only the X-ray glow, but the beam itself. When magnetic poles and rotation combine in the right orientation, the neutron star becomes a lighthouse. Its pulse can keep time across the galaxy, and many such pulses together can reveal motions in space-time too slow and broad for any single telescope image to show. A pulsar beam is not a lamp shining evenly into space. It is a narrow path of radiation shaped by rotation and magnetic field, crossing the darkness only where the geometry allows it. The neutron star may be sending energy outward in many directions through its magnetosphere, but the pulse that reaches a radio telescope depends on alignment. The beam must sweep across Earth, and Earth must be in the right place to receive it. This is why pulsars are both common and hidden. Many neutron stars may be pulsing somewhere in the galaxy, but most of their beams never pass across this planet. They rotate in silence from this point of view, not because they are inactive, but because their lighthouse never turns toward the observer. The ones that do point this way become clocks in the radio sky. The beam begins near the magnetic poles. These poles do not have to match the rotation poles. A neutron star can spin around one axis while its magnetic field is tilted at another angle. Charged particles are pulled from the surface or created in the magnetosphere, then accelerated along magnetic field lines. As they move through the curved field, they release radiation. The result is a beam tied to the magnetic field, carried around by the star's rotation. Each rotation brings the beam back. A flash arrives, then darkness, then another flash. The interval between flashes is the rotation period of the neutron star. For some pulsars, the interval is measured in seconds. For millisecond pulsars, it is measured in thousandths of a second. Their rotation is so steady that the arrival times of their pulses can be predicted with astonishing precision once the star's long, slow spin-down is understood. That steadiness turns pulsars into tools. A single pulsar can test the motion of a compact star, the pull of gravity in a binary system, and the flow of charged particles near a magnetic pole. A group of pulsars can do something even broader. Spread across the sky, timed carefully for years, they can become a galaxy-sized detector for very long gravitational waves. These waves are different from the short signals produced when stellar mass black holes or neutron stars merge. Those events rise and fade in seconds or minutes. Pulsar timing arrays search for waves with periods of years. They are slow, broad ripples in spacetime, expected from pairs of supermassive black holes orbiting in distant galaxies. Each pair moves through its long spiral, sending a faint gravitational murmur across the universe. The wave does not strike a telescope like light. It passes through space itself. As it moves, it stretches and compresses distances by extremely small amounts. The path between Earth and a pulsar changes slightly. The time taken by the pulse to arrive changes slightly with it. A single change would be too small and too easy to confuse with other effects. But many pulsars, watched together across many years, can reveal a shared pattern. This is the idea behind pulsar timing arrays. Radio telescopes monitor selected millisecond pulsars, measuring their pulse arrival times again and again. Each pulsar is like a distant clock. If all the clocks show tiny timing shifts with a particular relationship across the sky, the pattern can point toward a gravitational wave background. Not one wave from one event, but a low, persistent background made from many sources too distant and overlapping to separate. There is something almost still about this method. Nothing is photographed. Nothing is heard in the ordinary sense. A telescope receives pulses. A model predicts when they should arrive. The difference between prediction and arrival is measured, corrected, compared, and watched over long spans of time. The discovery is not a bright flash. It is a slow agreement emerging from years of patience. The precision required is severe. Pulses must be corrected for the motion of Earth, the orbit of Earth around the Sun, the motion of the pulsar itself, and the material between the pulsar and the telescope. Interstellar gas can delay radio waves depending on their frequency. The solar system's motion must be accounted for. The clocks on Earth must be stable. The pulse profile of the pulsar must be understood. Only then can the smallest residual timing shifts be examined. Millisecond pulsars are especially valuable because many of them are old and stable. Some were spun up by material from a companion star, gaining rotation until they turned hundreds of times each second. After the accretion ended, they remained as fast, quiet clocks, losing energy very slowly. Their pulses can hold a regularity that makes them useful across decades. In recent years, pulsar timing collaborations have reported strong evidence for a gravitational wave background at nanohertz frequencies. The signal is not from one nearby collision. It appears as a broad pattern across many pulsars, consistent with the expected hum from supermassive black hole binaries scattered through cosmic history. The word hum is only a metaphor, because no air is vibrating. Space-time itself carries the pattern. A neutron star, then, becomes part of an instrument larger than any observatory. The star supplies the clock. The galaxy supplies the distances. Earth supplies the telescopes. The gravitational waves pass through the whole arrangement, leaving their faint imprint in pulse arrival times. A compact remnant of a dead giant helps measure the motion of black holes far larger than itself. Pulsars also test gravity in closer systems. When a pulsar orbits another neutron star, its pulses carry a record of that orbit with extraordinary detail. The timing reveals how the orbit changes, how space-time curves, and how energy is lost through gravitational radiation. In some binary pulsars, the orbit shrinks at the rate predicted by general relativity. The pulses become evidence for waves that were once only a mathematical prediction. This gives the beam a second identity. It is not only radiation, it is a ruler, a clock, and a messenger. It carries information from the star's rotation, from its orbit if it has a companion, from the interstellar medium it crosses, and from the space-time through which it travels. Every pulse is simple in appearance and layered in meaning. The original lighthouse image remains useful, but it is incomplete. A lighthouse guides ships because its beam marks a location. A pulsar beam marks much more. It marks the spin of a collapsed star. It marks the shape of a magnetic field. It marks the motion of the star through the galaxy. In groups, it can mark the slow breathing of space-time itself. The beam keeps returning. Flash, silence, flash. Across the years, the rhythm is measured with care. Somewhere deep inside the star, superfluid vortices, superconducting currents, and magnetic fields all help sustain the system that makes the pulse possible. Far outside, the pulse becomes part of a quiet net stretched across the galaxy. The next step turns from timing back to light. Around a neutron star, gravity is strong enough that the surface cannot be seen in the ordinary way. Light leaving the hot regions does not simply travel straight outward. It bends around the compact body, carrying hidden parts of the star into view and allowing astronomers to measure the size of an object no telescope can resolve as a disk. A neutron star is too small and too distant for even the best telescopes to see as a round disk. It appears as a point, a pulse, or a source of X-rays against the dark. Its surface cannot be photographed in the ordinary way. No image shows continents of iron. No direct view shows the shape of its hot regions. Yet the star can still be measured, because the light leaving it does not travel through ordinary geometry. Close to a neutron star, gravity bends space strongly enough to bend the path of light. Photons leaving the surface follow curved routes as they climb away from the compact body. Some light that begins from the far side of the star can curve around the edge and still reach a distant observer. The result is quietly strange. A telescope can receive light from more than the half of the surface facing it. The star reveals a little of its hidden side. This does not mean the back of the star is seen clearly, like an object reflected in a mirror. The image is not direct. It is softened, distorted, and folded into the pulse of X-rays that arrives at the detector. But the effect is real. The stronger the gravity, the more the light bends. The amount of bending depends on the compactness of the star. The relation between how much mass. This turns light bending into a measuring tool. If a neutron star has hot spots on its surface, those spots brighten the X-ray signal as the star rotates. On an ordinary sphere, a hot spot would disappear completely when it moved behind the edge. On a neutron star, gravity can keep part of that light visible for longer than simple geometry would allow. The pulse becomes smoother, broader, and shaped by relativity. By modeling that pulse, astronomers can infer the star's size. NICER, the Neutron Star Interior Composition Explorer, was designed for this kind of work. Mounted on the International Space Station, it observes X-rays from rapidly spinning neutron stars. It records the arrival time and energy of individual photons with great care. Over many rotations, those photons build a pulse profile, a repeating pattern of brightness that carries the imprint of surface hotspots, spin, mass, radius, and gravitational light bending. The method is patient. It does not take a picture of the surface. It watches the star turn again and again. It measures how the hot regions rise into view, how they fade, how their light is delayed, and how gravity keeps some photons visible when ordinary sight would expect darkness. A model is built from many possible stars. The models that best match the pulses reveal what the real star may be. One of NICER's early targets was PSR J0030 plus 0451, a millisecond pulsar, not far by galactic standards. Its X-ray pulses allowed scientists to map hot regions on its surface and estimate its mass and radius. The surprising part was not only the size. The hotspots did not appear in the simplest expected places. They suggested a magnetic geometry more complicated than a neat dipole, with surface heating arranged in a way that made the star feel less symmetrical than the old classroom picture. Another important target was PSR J0740 plus 6620, one of the heaviest known neutron stars. Its mass is a little more than twice the mass of the Sun. That makes it especially valuable, because heavier neutron stars press their cores to higher densities. If dense matter becomes too soft under that pressure, such a star should not hold itself up. It would collapse further. If it remains stable, the interior must provide enough pressure to resist gravity. NICER's measurements found that this heavy pulsar has a radius broadly similar to the lighter pulsar measured earlier. The result narrowed the possibilities. Matter inside neutron stars cannot be too soft, or the heavy star would be much smaller, or would not survive. It also cannot be too stiff in every simple way, because other observations, including gravitational waves from neutron star mergers, place limits on how much the stars deform. The answer lies in a difficult middle. The surface pulse therefore reaches inward. A hotspot sends X-rays into curved spacetime. The photons arrive at a detector orbiting Earth. Their timing is compared with models. From that comparison, scientists learn something about matter buried far below the crust, in regions no light can leave directly. The measurement begins at the surface, but the question belongs to the core. This is one of the most graceful features of neutron star astronomy. The object is small, dark, and unreachable. The interior is hidden behind layers of iron, nuclear pasta, superfluid matter, and superconducting currents. Yet the star cannot hide everything. Its gravity bends its own light in a way that reveals how compact it is. Its hotspots turn with it, letting the surface write a repeating pattern across time. There are uncertainties. The atmosphere, if present, changes how X-rays leave the surface. Magnetic fields can alter the shape and temperature of hot regions. The exact geometry of the spots matters. The distance to the pulsar matters. So does the mass measured from radio timing or binary motion. Every model carries assumptions, and every assumption must be tested against the data. Still, the measurements have already changed the field. They have made neutron stars less abstract. Instead of speaking only about possible radii and theoretical equations of state, astronomers can compare those theories with light from actual rotating surfaces. The pulse profile becomes a bridge between observation and nuclear physics. A small, compact star bends light from its far side into view. A detector counts photons one by one. A model reconstructs the shape of invisible hot regions. From that slow work comes a constraint on how matter behaves at densities above those inside atomic nuclei. The process is careful, quiet, and deeply physical. The neutron star remains unresolved as an image. It is still only a source in the sky, but through its own gravity, it gives away its shape. The same curved spacetime that makes the star difficult to understand also makes measurement possible. Light climbs out, bent and softened, carrying with it the size of the body that released it. Beyond a single star, another kind of measurement waits. When two neutron stars orbit each other and finally merge, their matter is stretched by gravity, their interiors are tested in motion, and their collision sends both light and gravitational waves across the universe. In that event, the hidden density of neutron stars becomes part of the origin story of the heaviest elements found on Earth. Two neutron stars can spend a long time falling together. They may begin as two massive stars in a binary system, each one living quickly, burning through its fuel, and collapsing after its own brief life. One becomes a neutron star. Later, the other does the same. What remains is a pair of compact remnants, orbiting one another in the dark, each carrying more mass than the sun inside a body no wider than a city. They are small compared with the space between them, but their gravity binds the pair into a slow, tightening dance. The orbit does not stay fixed forever. As the stars circle, they send gravitational waves into space. These waves carry energy away from the system. The loss is tiny at first, but it never stops. The orbit shrinks. The stars move faster. The time between each turn becomes shorter. Across millions or billions of years, the pair draws closer, as though the wide darkness between them is being quietly folded away. Near the end, the motion becomes rapid. The two stars sweep around each other many times each second. Their shapes begin to respond to one another's gravity. Each star raises tides on the other, not ocean tides, but distortions in matter at nuclear density. How much each star deforms depends on how stiff its interior is. A softer star stretches more. A stiffer star resists. The final orbit, therefore, carries information about the hidden matter inside both stars. Then the surfaces meet. For a brief moment, the boundary between two neutron stars disappears into one violent region of dense matter, heat, gravity, and magnetic field. The collision is not only an explosion of light, it is a laboratory that exists once and then is gone. Matter is squeezed, torn outward, heated, and flung into space. Some material remains in a central remnant that may become a heavier neutron star for a short time, or may collapse into a black hole. Some escapes. The escaping material is the key to one of astronomy's old questions. Stars make many elements by fusion. Hydrogen becomes helium. Helium and heavier nuclei can build carbon, oxygen, silicon, and iron through different stages of stellar burning. But the heaviest elements require a different path. Gold, platinum, uranium, and many rare elements need a flood of neutrons. Atomic nuclei must capture neutrons faster than they can decay. This is the rapid neutron capture process, often called the R process. A neutron-star merger supplies the conditions. Dense neutron-rich matter is ejected from the collision. As it expands and cools, nuclei inside it capture neutrons in great numbers. Those unstable nuclei then decay toward more stable forms, building heavy elements that ordinary stellar fusion cannot easily produce. The light from the event is powered by the radioactive decay of this newly made material. That glow is called a kilonova. In August of 2017, gravitational wave detectors observed such an event. The signal was named GW17-0817. It came from two neutron stars spiraling together in a galaxy about 130 million light-years away. The gravitational waves reached Earth first as a stretch and squeeze in space-time, measured by laser interferometers. Less than 2 seconds later, a gamma-ray burst arrived from the same region of sky. That short delay linked the waves and the light. Telescopes across Earth and in space turned toward the source. They found a fading optical and infrared glow in the galaxy NGC 4993. In the first hours and days, the light changed color. It began relatively blue, then reddened as heavier material shaped the emission. The behavior matched expectations for a kilonova, where R process elements form and decay in expanding debris. Spectra from the event carried signs of heavy element production. Later analysis identified strontium, and the broader infrared glow supported the presence of lanthanide-rich material, the kind expected when neutron-rich debris builds heavy R process elements. The exact amounts of each element remain model-dependent, but the event showed directly that neutron-star mergers are major sites where heavy elements can be made. This gives the collision a strange intimacy. The gold in a ring, the platinum in a device, the rare elements hidden in Earth's crust did not begin on Earth. They were made before the solar system existed, in events that seeded interstellar gas with heavy atoms. Some of that enriched gas later became the sun, the planets, and the small solid world where those atoms could settle into rock, metal, water, and life. A neutron-star merger is therefore both distant and local. It happens in another galaxy or in the ancient past of this one, but its products can end up in a human hand. The connection is not symbolic. It is material. Heavy atoms are travelers across cosmic time. The gravitational waves from GW17-0817 also revealed the stars before they touched. The signal contained the masses of the two objects and hints of their tidal deformability. That deformability is a measure of how much each star was stretched by the gravity of the other during the final inspiral. Since the stretching depends on the stiffness of neutron star matter, the wave carried information about the equation of state, the relationship between pressure and density inside the star. The light added more. The gamma-ray burst showed that at least some neutron star mergers can produce short gamma-ray bursts. The kilonova showed heavy element synthesis. Radio observations over the following months traced the outflow as it moved into surrounding space. X-rays added another part of the same story. This was multi-messenger astronomy. Gravitational waves, gamma rays, visible light, infrared light, X-rays, and radio waves all describing one event from different angles. Each messenger told a different truth. Gravitational waves described the orbit and the compact masses. Light described the debris, the outflow, and the freshly made elements. Together, they made the event richer than either signal alone could have been. The merger also showed why neutron stars matter beyond their own surfaces. They are not only remnants. In pairs, they become engines of chemical creation. The dense matter that once sat locked inside a compact star can be thrown outward, broken apart, rebuilt into heavy nuclei, and scattered into space. The star that seemed like an end becomes part of a beginning somewhere else. After the glow fades, the atoms remain. They drift through galaxies. They mix with gas clouds. They enter new generations of stars and planets. Some settle deep into planetary crusts. Some become dust. Some become the quiet metallic trace inside living worlds. The collision is brief. The material legacy lasts far longer. Yet even the merger does not reveal everything. It tests the stars through motion, deformation, heat, and light. But the deepest center of a neutron star still avoids direct view. The waves narrow the possibilities. The kilonova shows what escapes. The surface pulses show how light bends. Still, the core itself remains hidden behind layers of dense matter. Waiting is one of the most difficult questions in modern physics. The deepest part of a neutron star cannot be reached by light. No photon from the inner core travels outward to show its condition directly. The surface sends X-rays. The magnetic field shapes pulses. Gravitational waves carry the memory of tidal stretching during a merger. Each signal approaches the center from outside, narrowing the possible answers. But the core itself remains enclosed by the star's own density. Above it, the layers have at least some connection to known physics. The crust can be described with nuclei, electrons, and free neutrons. The pasta layer can be modeled with nuclear forces acting in compressed geometry. The outer core can be treated as a dense fluid of neutrons, protons, and electrons, with superfluidity and superconductivity, changing the way those particles move. These states are strange, but they still have points of contact with experiments and theory built on Earth. The inner core is different. There, density may rise to several times the density inside an atomic nucleus. A nucleus is already matter pressed into one of its most compact ordinary forms. Inside the center of a neutron star, the particles are packed even closer. The distances between neutrons become so small that the familiar picture of separate particles may begin to fail. The question is no longer only how neutrons behave under pressure. It is whether neutrons remain the right objects to describe. A neutron is not elementary. It is made of quarks, bound together by gluons through the strong force. Under ordinary conditions, quarks are confined. They do not wander freely outside protons and neutrons. They are locked inside those larger particles, and all of chemistry, nuclear structure, and ordinary matter rests on that confinement. But at the densities expected in the inner core, the boundaries between neighboring neutrons may become less distinct. Quarks might begin to move through a larger region, forming a phase of matter unlike the neutron fluid above it. This possible state is often called quark matter. It is not known to exist in neutron star cores, but it is one of the serious possibilities. In such a phase, matter would no longer be built from separate neutrons packed side by side. The quarks inside them could become partly deconfined, sharing space across the dense medium. The star would still be held by gravity and pressure, but the source of that pressure would come from a deeper level of particle physics. There are other possibilities. The core may contain hyperons, heavier cousins of protons and neutrons that include strange quarks. Under high enough pressure, creating these particles may become energetically allowed. At first, that seems natural. Dense matter can reduce its energy by opening new particle states. But hyperons create a problem. In many models, once they appear, they soften the equation of state, meaning the matter provides less pressure at a given density. If the core becomes too soft, it may not support the heaviest neutron stars known. This is the hyperon puzzle. Observations show that some neutron stars have masses around 2 times the mass of the Sun. Any model of the inner core must allow such stars to survive. If hyperons appear and remove too much pressure, the star would collapse into a black hole before reaching those masses. The particles may still be present, but if they are, the forces between them must provide enough extra support. The puzzle is not only whether hyperons exist, it is how dense matter remains strong enough if they do. Another possibility is that exotic condensates form. Certain particles, under extreme density, might occupy the same quantum state in large numbers, creating a collective phase of matter. These ideas include pion or kaon condensates in some models. The names come from particle physics, but the meaning in the star is simple enough. When pressure changes the energy balance, matter may find a new arrangement that does not occur in ordinary nuclei. The core becomes a place where the lowest energy state of matter may be something no direct experiment has held for long. Each possibility changes the equation of state. This phrase describes how pressure responds to density. If dense matter is stiff, pressure rises strongly as it is compressed. A stiff star can support more mass and tends to have a larger radius. If dense matter is soft, the star compresses more easily and may be smaller, with a lower maximum mass before collapse. The equation of state is the hidden rulebook of the neutron star. It cannot be read directly from the core, so astronomers read it from the outside. A heavy neutron star proves that the equation of state cannot be too soft. A radius measurement from X-ray pulse modeling limits how large or small the star can be. A neutron-star merger shows how easily the stars stretch before contact. The cooling of young neutron stars offers clues about which particles carry energy away. None of these observations alone gives the whole answer, but together they press inward on the range of possibilities. There is also the speed of sound inside dense matter. In ordinary language, sound means vibration traveling through air. In physics, it is a pressure disturbance moving through a medium. The speed at which such a disturbance travels depends on how stiff the matter is. In a neutron star core, this speed may become a large fraction of the speed of light. It cannot exceed light, but how close it gets tells physicists something about how strongly the matter resists compression. This matters because some observations seem to require dense matter, that is soft at certain densities and stiffer at others. A star must be compact enough to match radius constraints, yet stiff enough to hold two solar masses. This suggests that the interior may not follow one simple rule from crust to center. The equation of state may change character with depth. A transition to quark matter, hyperons, or another phase could leave an imprint in that pattern. The center may therefore contain a boundary no telescope can see, not a crust, not a surface, but a phase transition inside the core. Above it, matter may behave mostly as neutrons and protons. Below it, another state may take over. The star would still appear as one object from outside, still rotating, pulsing, cooling, and bending light. Inside, it could hold a hidden change in the identity of matter itself. The honest answer is that no one knows which picture is correct. The observations have become better, and the room for models has become smaller, but the center has not yielded completely. Some equations are now disfavored. Some ideas survive. Others wait for stronger data from future X-ray telescopes, more massive pulsars, and more neutron star mergers detected through gravitational waves. This uncertainty is not a failure of the story. It is the place where the story remains alive. A neutron star is one of the few natural objects where gravity can press matter close to the limits of nuclear and particle physics without hiding everything behind an event horizon. It is visible enough to measure, dense enough to challenge theory, and stable enough to last across cosmic time. At the center, the pressure of a dead giant still holds. The particles may be neutrons, or quarks, or something arranged in a form not yet named with confidence. Around that unknown core lie the superfluid ocean, the pasta layer, the dripping neutrons, the crystalline crust, the magnetic field, and the beam that crosses space. The star is small in the sky, but inside it, the map of matter is unfinished. The journey inward ends there, not with a wall, but with a question held under gravity. The question at the center does not end the journey, it widens it. A neutron star cannot be opened, but it can be approached from many directions at once, by light, by timing, by waves in spacetime, and by the slow cooling of its surface. Each method touches a different layer. None of them alone can name the core. Together, they begin to draw the outline of what the core cannot show directly. A radio pulse gives one kind of clue. Its rhythm carries the rotation of the crust and the behavior of the magnetic field. When that rhythm changes, even slightly, something inside the star has shifted. A glitch may point towards superfluid vortices unpinning below the crust. A long-term slowdown may reveal how magnetic energy is being carried away. A pulse that arrives early or late by a tiny fraction may contain the trace of internal motion hidden beneath the surface. X-rays give another clue. They come from hot regions on the crust, from magnetic activity, from accreted matter, or from heat leaking out of the interior. Their brightness and energy reveal surface temperature. Their timing reveals rotation. Their shape across a pulse reveals the way gravity bends light around the star. When the same hot region stays partly visible after it should have moved behind the edge, the star is quietly measuring its own compactness for anyone able to read the curve. Gravitational waves add a third path. In a merger, two neutron stars test one another before they touch. Their gravity stretches each other, and the amount of stretching depends on the stiffness of the matter inside. A star with a softer interior yields more easily. A star with a stiffer interior resists. The final spiraling signal carries this difference in its shape, encoded not as light, but as a change in distance smaller than any ordinary instrument could notice. The merger light then tells what escaped. Blue light, red light, infrared glow, radio afterglow, and X-rays can describe the debris thrown outward and the remnant left behind. If the merged object collapses quickly into a black hole, the signal may differ from a remnant that survives for a short time as a massive neutron star. The lifespan of that remnant, whether brief or extended, is another clue to how much mass dense matter can hold. The core is therefore being surrounded by evidence. From one side comes the radius of a quiet pulsar. From another comes the mass of a heavy neutron star in a binary system. From another comes the tidal deformability of merging stars. From another comes the cooling of young remnants. From another comes the timing of old millisecond pulsars spread across the galaxy. The center remains hidden, but the possible shapes of its physics are pressed from all sides. This is how modern astronomy often works with the invisible. It does not always reveal an object by seeing it plainly. It limits what the object can be. A model that makes a star too small is set aside. A model that cannot support a two-solar mass neutron star is weakened. A model that predicts too much tidal stretching must face the merger data. A model that cools too quickly or too slowly must face the X-ray surface. The truth is approached by removing the impossible. There is patience in that process. It is not a single answer arriving all at once. It is a narrowing. The allowed region becomes smaller. The uncertainty changes shape. A theory that once seemed broad must become more careful. A measurement that once seemed distant becomes precise enough to matter. The neutron star, silent in its own place, is slowly translated into numbers that describe pressure, density, radius, mass, and time. Future observations will continue that translation. More heavy pulsars may be found. More mergers may be detected. More X-ray pulse profiles may be measured. Longer timing records may turn millisecond pulsars into even more sensitive clocks. Each new star adds another point to the map. A single neutron star is valuable. A population of them is stronger. Together, they show how dense matter behaves across different masses, ages, magnetic fields, and histories. Some stars are young and hot, still close to the supernova that made them. Some are old and faint, cooled through ages of quiet radiation. Some live alone. Some pull gas from companions and flare in X-rays. Some spin slowly with strong magnetic fields. Some spin hundreds of times each second with remarkable stability. Some collide and seed space with heavy elements. Each kind is a different experiment performed by nature with the same basic material under different conditions. This variety is not a distraction. It is the reason the hidden core can be studied at all. A single object might allow too many interpretations. Many objects begin to separate them. A soft equation of state may match one radius, but fail another mass. A phase transition may explain one pattern in cooling, but must also survive the merger constraints. A model with quark matter must still account for pulsars that remain stable at high mass. Dense matter has nowhere to hide completely when many stars are measured in many ways. And yet, even with all of this, the neutron star keeps something of its mystery. It does not become ordinary because it can be modeled. The model itself points to how far from ordinary the object is. Matter there is not arranged in the familiar language of stone, air, water, metal, or flame. It is arranged by nuclear forces, quantum pressure, gravity, and rotation. The star is compact, but the physics inside it is wide. A neutron star begins as the remnant of collapse, but it becomes more than debris. It becomes a clock when its beam crosses Earth. It becomes a map when X-rays bend around its surface. It becomes a detector when its pulses reveal gravitational waves. It becomes an element maker when it merges with another star. It becomes a laboratory when its core forces theory to face densities no laboratory can hold. The path inward has passed through every layer that can be named with confidence and into the region that cannot yet be named fully. The answer may include neutrons packed to their limit. It may include hyperons. It may include quarks no longer confined inside individual particles. It may include a transition not yet recognized clearly in the signals. The star does not say which one plainly. It gives light, timing, heat, and waves, and waits for them to be understood. For now, the center remains covered. Above it, the outer core moves in superfluid vortices. Above that, the pasta layer holds its strange geometry. Higher still, neutrons drip from nuclei in the inner crust. The iron skin radiates in X-rays. The magnetic field reaches outward, shaping particles and beams. The pulse crosses space, steady enough to measure the smallest disturbances, patient enough to keep returning long after the supernova has faded. A neutron star is small only to the eye. In meaning, it is immense. It is the border between a star and a black hole, between atomic matter and something deeper, between known physics and the part still being tested. It carries the memory of a giant star, the weight of a sun, the rhythm of a clock, and the silence of an unfinished core. The journey can now begin to drift away from it, leaving the dense remnant where it is, still turning in the dark. The view begins to widen. The neutron star remains where it is, turning quietly beneath its own gravity, its surface too small to resolve, and its interior too deep to open. The pulse still moves outward. The X-rays still leave the iron skin. The magnetic field still draws invisible curves through the space around it. Nothing has to hurry. Farther away, the remnant becomes a point inside a larger darkness. The old supernova cloud has thinned into faint threads, drifting through the galaxy with the slow patience of dust and gas. Somewhere in those threads are atoms that once belonged to the star, carried outward after the collapse, waiting for another cloud, another system, another long future. The dense core keeps its question. Neutrons, quarks, hidden phases, pressure, and gravity remain folded into the center, beyond direct sight. The answer does not need to arrive tonight. It can stay there, held in the quiet weight of the star, while the signal continues to cross the dark. The journey now drifts back from the surface, back from the curved light, back from the radio beam and the slow waves in space-time. The star becomes smaller. The galaxy opens around it. Other points of light appear, each with its own age, its own heat, its own silence. The mind can let them pass without counting them. There is only distance now, a soft field of stars, a remnant cooling in the dark, a pulse too faint to follow. The universe holds all of it without effort, the known and the unknown, the measured and the unfinished, the bright surface and the hidden core. The body can rest, the room can stay still. The stars continue slowly, far away, with no need to be understood all at once. Is greater than, is greater than, is greater than. End of script. Sleep well.